Sure. Your name tags out, all the usual good stuff. Beta your name tag. Don't forget your name tags. I don't know who you are. The class is very. I'm hoping more people turn up. Okay, 12:30, let's begin. Can you shut your laptop, lady at the back? Thank you. And since the class is so sparse, can you do me a favor? Everybody come up to the front so that I don't have to yell. And also we get to see exactly how poor the attendance is. When you scatter yourself across class, you give this fake impression of having a full class. So please, come on up. And bring your name tags, right? And while you're doing settling down, I'm going to keep talking. Okay. So Thomas, where did we leave off? finding alignments for sequence-to-sequence models, and we spoke of a specific, what was the basic problem we were dealing with in the last class? So Eli.
So we're looking for ways of aligning the model without doing the n-squared algorithm. So spend a lot of time in
But what was the problem itself? What kind of alignment data problem we were looking at?
like asynchronous outputs.
So we were looking at the problem of asynchronous outputs, right? This was a problem of sequence-to-sequence modeling. A sequence x1 through xn goes in, a different sequence y1 through ym comes out. And these kind of problems occur, for example, in speech rec. Uh-oh, I hope your laptop's okay. So where speech goes in, a word sequence comes out, or in machine translation, one word sequence goes in, a different word sequence comes out. Dialogue systems, a user's response goes in, the input goes in, the system's response comes out. Question answering, a question goes in, an answer comes out, and so on, right? In general, the number of symbols in the output sequence need not have any relation to the number of symbols in the input sequence. So you can have different kinds of problems. In the simplest problem is where you have one output for every input. We know how to deal with it. And so very often we try to sort of convert everything to a form into that form simply so that we can deal with it using standard techniques. But there's no such guarantee. And so you have problems where the order of the output corresponds to the order of the input. So if speech went in and the output was I ate an apple, then the portion of the input that corresponds to I precedes the portion of the input that corresponds to 8 because I comes before 8 in the output. On the other hand, if you look at something like machine translation, I ate an apple, and the German translation is Ich habe einen Apfel gegessen. So you have to get all the way to the end before you realize what the person did to the apple. So in that case, there's no order correspondence between the input and the output. In fact, you don't even have any correspondence between the number of symbols in the output and the number of symbols in the input. And a single symbol in the input may map to two very separated symbols in the output. For example, 8 goes to habe and gegessen, right? And they are separated by several words. So, and you can have things like a dialogue system where the question, the what goes in might be a question, and the answer that comes out may have nothing at all to do with your input. So your question is, my machine's showing a blue screen. And the answer is, did you try rebooting it? There's no correspondence at all. So we have different kinds of problems. Now, we are going to be dealing with the speech recognition problem, but this is just an example of a particular class of problems where the output sequence has an order correspondence to the input. Now, here, the input and output sequences happen in the same order, but they are not time synchronous. So they cannot be aligned. They can be sort of aligned against one another, but you don't have an output for every input. The problems we saw here were how do we perform inference on such a model, how to output time asynchronous sequences, and the second one was how do we train such models. And we partially addressed this problem by just saying I could just pick the most likely symbol at each time and collapse all of those repetitions into a single instance. Now, we spent a little more time on how to train such models. And the idea here was that if you were given the alignment, your training data are going to comprise inputs and the corresponding outputs. So the input would be of some length, and the output is going to be typically of a different length. But if you were given the information about where in the input each output must be generated, that is, if you were given the alignment of the output to the input, then training was easy. You could just compute the divergences at the specific time instance where the output was supposed to be generated, or even repeat things and fill out the sequence and convert it to a time synchronous problem. And we also saw the logic behind doing this. You do not want to ignore the outputs where, which don't correspond to the output symbols. You want to assume that an output symbol actually sort of stretches through the entire sequence that generates it. And so you just repeat the symbol, and now you have an order aligned You have a time synchronous output, and then you can define a divergence, and the divergence is simply going to be, in this case, the sum of the divergences at individual times, which we saw if you're using a one-hot representation, that's going to be the sum over time, the negative of the sum over time of the log of the likelihood assigned to the target symbol by the network. So everybody remembers all of this, right? Now, what is the key component of trying to perform back propagation? We need to be able to compute the gradient of the divergence with respect to the network outputs, right? Guys, can you shut your laptop? Thank you. So, and so that means that we need the gradient of the divergence with respect to every single output vector. We also saw that at any time, the network doesn't just output a symbol, it outputs a set of probabilities, a probability for every output. And so the gradient really tells you how much does perturbing the output, any single output, change the loss. And we found that when you're using the KL divergence, then the loss itself only considers the log likelihood of the target symbol. The other symbols are not considered. So if you look at the derivative of the divergence with respect to the output at any time, that would be a vector where most of the components of the vector are 0, and there's a single component corresponding to the target symbol. And the value of that component is going to be -1 over the probability assigned to that symbol by the network, right? So the bigger problem was, what do we do when the alignment is not provided? In this case, I have no idea where the outputs must be generated, so I can't compute this divergence or the derivative. So here, we came up with a solution. We said, let's guess the alignment. I'm given the symbol sequence. Let me take some guess as to where in the input, at what input times each of these output symbols must be generated. And then once you guess an alignment, you can use that guessed alignment to actually compute the divergence and train the network. But this alignment is guessed. It's not likely to be the right one. So you can use the trained model to go back and refine the alignment. And we saw that we can do this using the Viterbi algorithm. And then you can use the refined alignment to go back and retrain the model. So for one. Okay, 5 seconds, guys. All right. Anybody want to answer the first question? Harini? True. And Lihan, what about the second one? Yep. So Viterbi training explicitly estimates the alignment of each training instance and computes the divergence for the estimated alignment. And you require re-estimation of this alignment at each iteration because within each iteration, your model has improved and it's capable of giving you a better alignment. What was the problem with this approach, Denise? What was the problem?
Oh, for this one?
Yeah.
Okay, so. Wait, which one? For the first one or the second one?
The general approach of how we said we would train the model in the last class.
Oh, I mean, the first one, if we just align at the beginning and then train the model on top of it, like we do not make incremental upgrades, into it?
Well, even if we update the alignment, what happens? Anybody else? He just came in. I'm just bullying him. Okay. So what was the problem with this approach? Anybody? Yeah.
Initial alignments were like terrible because the model was not great.
So because you're very heavily dependent on the initial alignment, you're prone to local optima. Now, this still works very nicely if you have gobs and gobs of data. But if you have anything less than gobs of data, then you really want to do something smarter. And so instead of guessing the alignment, we know that how to train if the alignment is provided. We've just seen this in some detail. The problem is that the alignment is not provided. We could have guessed the alignment, but we saw issues with it. So now, what is the alternative? Let's consider all possible alignments. So let me give you an example. Let's say I have an input that is exactly 6 time instance long, x1 through x6. And I know that the symbol is AB, right? Just the symbol sequence is just AB. How many different ways do I have of aligning the symbol sequence here? I said this sequence to the input. In this case, anybody? 6, right? I can have A followed by 5 Bs, or I can have AA followed by 4 Bs, AAA, followed by 3 Bs, AAA, followed by 2 Bs, and A, 5. Only 5, not even 6, right? These are the only 5 ways of aligning that input to the input. When I perform my training over here, which of these alignments am I choosing? The most likely one. So what we really have is that you have these 5 possible ways of aligning. So each of these, you have A1 through A5. You have 5 possible ways of aligning the input, the symbol sequence to the input. And each of them has some probability, right? And so this would be PF aligned, right? And we picked the most probable alignment and use that, yes.
How's that probability calculated?
We saw that in the last class. What was the how was the probability calculated? It was the product of the probabilities of all the symbols in the alignment, right? We'll get back to it. Yes, and what we did was to actually pick the most likely alignment. Now, to answer your question, the way we did this was we first we took the network table of probabilities output by the network. We pulled out the rows corresponding to the symbols in our sequence. We composed this compressed table of probabilities, which only included the symbols in our training instance and in the proper order. And the probability of any given alignment was just the product of any alignment was a path through this table from the top left corner to the bottom right corner. And the probability of the alignment was just the product of the probabilities on the entire path. So we saw, and we picked the path with the largest probability, right? And we found that the divergence that you would get if you chose the most likely alignment is the negative of the sum over time of the log of the probabilities assigned to the individual instance, individual symbols in this best alignment. Now, this is picking just the most likely alignment, and we saw there are some issues. What would be a nicer way of doing it? What would be a more gentle way of not committing to a single alignment? Anyone? Yeah.
Soft assignment?
Soft assignment. How would you do that?
I guess we have to like hold on to the probabilities of the assignments as well, right?
So what you would want to do, Denise is absolutely right. Corresponding to each of these guys, you can compute a loss, right? Every one of these alignments is going to give you a loss. And then you can just take the average over all of these alignments, where the weight assigned to any alignment is the probability of the alignment itself. That's your soft assignment. Now you're not committing to a single alignment. You're just taking the average over all possible alignments, the weighted average over all possible alignments. Is that making sense to everybody? Right. And so The alternate view here is that there's a probability distribution over alignments of the target symbol sequence to the input. Selecting a single alignment is the same as randomly drawing a sample from this alignment, except that we're not randomly drawing the sample, we're drawing the most likely sample. And so instead, of using just the most likely alignment, I can use the average, the soft assignment. I can use a weighted average of the losses computed using all possible alignments, where the weight for each alignment is simply the probability of the alignment itself. This is basically the same as taking the expected loss over all possible alignments, right? So you're considering every alignment and you're taking the expectation, the average over all possible alignments. Is this equation making sense? What I have in the square bracket is simply the loss associated with any particular alignment, which is the sum over time, the negative of the sum over time of the log probabilities assigned to each symbol in the alignment, right? But here's what I can do. So what would be the problem with this guy, with this? Yeah.
The number of alignments if growing exponentially.
The number of alignments grows exponentially. So obviously you can't do this in a naive manner, right? How can I simplify this? Yeah.
Maybe you consider just like a smaller sequence, like only 10.
You're getting into engineering solutions. The math is staring you in the face, right? What I can do, well, give you a poll. That's what I can do. 10 seconds, guys. Okay, time's up. Someone on Zoom, can you answer the first question? Is there anybody on Zoom?
True.
Okay. True. And what about the second one over here, Kyle?
False.
Okay, it's already answered for you, right? Anyway, so the training without alignment procedure computes the average divergence over all possible alignments. This is true. Also, because you're taking the average over all possible alignments, you don't need to choose an alignment. There's no explicit commitment to any single alignment that you choose. But then the problem is there are an exponential number of possible alignments. How do you deal with this? This is where we actually look into the formula for the alignment itself, the loss for any given alignment itself. The formula for the loss for any given alignment is the negative of the sum over time of the log probabilities assigned to every single symbol in the sequence, right, in the alignment. Summation is linear. So that means I can move the expectation in, right? And so this is simply going to say this is now the negative of the sum over time of the expected log likelihood of the probability assigned to any symbol. So what is that crazy second term? The term inside the expectation. Now, when I was given the symbol sequence AB, I actually ended up computing this table, right? And let's just say I have ABC to make this more explicit. So I actually ended up computing this table, and I was looking for paths of this kind, right? This is what I was looking for. But this, if you consider this table, every single node in the table has a probability associated with it. So you want to take the expectation of this log probability. What is this expectation? What is this crazy value? Now, when I compute an alignment from the top left corner to the bottom right corner, is every alignment guaranteed to go through this node? No, right? So what fraction of them go through this node? So this means that every node is not just simply a node by itself. There is a probability that if you actually, every path has a probability associated with it. There is a probability that the alignment goes through the node. Correct? And so every one of these three nodes over here would have such a probability. And so this expectation over here, this term, of course, this is it's the weighted sum of the log probabilities in this column, where the weight assigned to any given node over here is the probability that an alignment will go through the node. Is that making sense? You're looking confused. Right? Yeah.
But the probability of like a path going through that point depends on the probability of its parents.
Thank you. We'll get to that. Yes. So if you look at all possible ways of aligning this guy to this one, right? There are many different possible ways of aligning the input to the output to the symbol sequence, and only some small fraction of those go through this node. So you're going to, and so the probability that an arbitrarily drawn alignment will go through this node is this posterior probability. You multiply that by the log probability of the log probability in the node itself. You sum it over the entire column, sum this term over the entire column, and that is this expectation over here, the expectation of the log probability of the node. Okay, so now we are left with this other challenge. How do you compute this probability? How do we compute the probability that an arbitrary alignment goes through this node? Yeah.
Why are you taking the sum over the column?
You're taking the expectation, right? So at each time, these are the only nodes, and these are the only symbols on the in the input. So we have to sum over all of these symbols, correct? That's the column.
So you're basically grabbing your probability from the probability that your path runs through that particular section of the table, and you're taking that over the sum of all the columns.
Yeah, so the sum over all the entries in any column. So this outer summation, the summation over T, is the sum over sum in this direction, and the inner summation is the sum this way. So you're summing over the entire table, okay? So now how do we compute the posterior probability that an arbitrary path goes through this node? Now this probability, the probability that we are really looking for is the probability that given the input and the symbol sequence, ABC in our example, any particular alignment goes through this particular node. So given that the input is this set of vectors and the corresponding sequence is ABC, what is the probability that the third input is going to be aligned to the symbol B? That is what that probability computes. Now remember, if I just gave you the input, the 6-hex sequence input, symbol input, how many possible sequences can I generate from it? We know that it's an arbitrary number. ABC is not the only sequence that you can generate from it, right? So we want the conditional probability. Given that the sequence is ABC, what is the probability that the second symbol is aligned to B? Now, that is proportional to the joint probability. The joint probability is the probability that this input corresponds to ABC and the second symbol has been aligned to the third input. So you can just use Bayes' rule. I can say P of S, the ST equals SR given uppercase S is proportional to P of ST equals SR and uppercase S. That's just simple Bayes' rule, right? And now that term to the right can be computed. Now look at this example. If I'm looking at the posterior or the probability of generating the symbol, of having the symbol sequence be beefy, and that the fourth input, T equals 3, aligns to the symbol E. That is the probability of all alignments which align X3 to E, right? That is the total probability of the entire subgraph of alignments shown by the blue arrows, the entire subgraph that goes through the highlighted box, which aligns the third input to the symbol E, right? Yeah. I'm saying everything that's shown with the blue arrows. So everything with the blue arrows represents every symbol, every possible alignment that aligns E to time 3, right? There's no other path that's not represented in that graph. Right, yeah. So it's no, if I'm aligning the symbol, what is the probability of this symbol sequence and aligning symbol E to time 3? Is the entire graph constrained to the fact that the graph goes through this path, right, through the highlighted node? Yeah.
Why is the probability of the node, which is E at times 3, dependent on the path that it takes in the future?
It's the posterior probabilities, right? So you're saying what is the probability of an alignment? So again, what was the probability, the question we're asking? If I randomly selected an alignment from the set, what is the probability that it's going to align this guy to this, right? The probability of an alignment is the entire seek path, is it not? Right. Yeah. Yeah, because you're multiplying more stuff to it, right? Yeah. Okay. So is this graph making sense to all of you guys? Any questions? Because we're just going to use everything, or base everything off of this graph, okay? And so I need to get in order to compute the posterior probability that the third input aligns to the symbol E, I need to compute the probability of this pink portion of the graph. And that is easy enough, right? I can decompose it into two portions. The entire graph that comes into the node and the rest of the graph that goes out of the node. So the probability of, so this is like the probability of aligning B to the input sequence that ends at time 3, right? And the probability of aligning EFE, right, to everything else, given that the initial portion was aligned to B, right? So if I look at this, you can see how this pink graph can be decomposed into the blue graph and the red graph, right? So the probability of the total graph, Bayes' rule, is going to be the probability of the graph in the blue box times the probability of the graph in the red box, given that the early portion of the input fell in the blue box. That's Bayes' rule, right? Questions? Yeah.
So the transition probabilities of the edges,
They're all 1. That's how we have, yeah.
right? Yeah.
That's how we set it. Yeah. And then once we break it up this way, we have to make one more observation. The probability that the inputs 4 through 8 are aligned to EFE, does that depend on the specific alignment of the first 3 inputs? It does not, right? And because so long as you know that the third that it falls, the alignment must fall somewhere within the red graph, you don't care exactly which path you took within the blue graph. And the reason for it is very simple. It's something called conditional independence, that when you compute your probabilities, the Y's are dependent only on the input. From the input, you compute the hidden layer values. From the hidden layer values, you compute the probabilities. And those probabilities are just fed to your dynamic programming block. The alignment that you choose is never fed back to compute the probabilities at the next time, right? If I had somehow considered the fact that the second input aligned to the symbol E when I was computing probabilities for the third input, then there's dependence. When I'm not considering the fact, when the probabilities are being computed by the neural network without considering the alignment, then the two graphs are basically not dependent on one another. The table of probabilities has already been generated. That means I can compute the probabilities of those two graphs independently, right? And so this means that the total probability of the highlighted graph is going to be the probability of the red portion of the graph times the probability of the blue portion of the graph. That making sense to everybody? So Kofi, making sense? Okay. So let's do this. How do you compute this probability? Now let's focus on the first part. the pink graph. I'm going to call this the forward probability because it's the forward it's the all forward paths until the highlighted node, right? Now, if you want to look at this guy, this is the graph whose probability I want to compute. Basically, I want to compute the set of the total probability of all paths through this portion of the graph, which ends with the symbol E at time 3, right? I'm going to represent that as alpha TR. In this case, it's going to be alpha 3, 2 or alpha 3E. Is the total, this alpha term is the total probability of all paths that end at the rth symbol at time t, okay? Now, how do I compute that? Can anybody tell me? Can anyone take a guess? Yeah. You need recursion, right? This node, the node at 3E, can only be arrived at either from the pink node or the green node. Those are the two parents, right? So the total probability of all paths that end up at this node, since there are only two ways of arriving here, that's going to be the total probability of all paths that end up here and the probability of extending that by this node. That's going to be the probability of this subgraph times y3e plus the total probability of all paths that end up here times the probability of extending that by this extra symbol. So it's the total probability of this subgraph times y3e, right? So what is the total probability of this subgraph in terms of our symbols? Pardon me?
You keep going backwards till.
That's so if alpha TR is our representation for the total probability of any of all paths ending at a particular node. So this is going to be alpha 3e, right? And the total probability of all paths ending here is going to be alpha 2b, correct? The total probability of all paths ending here is going to be alpha 2e. And so just adding that, that's simply going to be the alpha 3e is going to be alpha 2b times y3e plus alpha 2e times y3e. Is making sense to everybody? Everyone, any questions? No, okay. And so this means that the general formula for alpha TR is the sum over all parents of this TRth node of the alpha for the parent times YTR, right? And all the parents are at time t minus 1. That's all. Making sense? Okay. And so just writing this is our simple recursive formula. Very simple, right? Now let's see how this thing can be computed for every node in the graph. Is that making sense? Yeah.
Just a quick question. What's the probability, like, how do you calculate the probability of the transitions? You might cover it.
The transitions are all 1. We just assign them a probability of 1, right? All the edges have a probability of 1.
How are they all 1? Because then,
So we're just saying that the probability of any particular sequence is the product of the probability of all the symbols in the sequence, right? So that implicitly means that the edges have a probability of 1. That's how you said.
so like, if all the edges have probability of 1, would you calculate the probability of getting to the end? Just still 1. You should multiply by 1.
No, because all the nodes have probabilities that are not 1.
Gotcha. Okay, cool.
Right? So, okay. So alpha TR is the total probability of the subgraph shown over here, right? And is the sum over all of the parents of the alphas for the parents times YTR, right? So I can just write it up this way. It's the sum over all the parents of the alphas for the parents, whole thing multiplied by the probability of the node itself. So how would you compute this? Let's say I have this entire graph. Then at the very first time, I know that the graph must begin at the top left node. So the total probability of all paths that begin at the top left node is simply going to be the node probability itself. All the other nodes in the first column are not possible as the first node in any path. So the blacked out nodes are going to have a probable alpha score of 0, right? Then at the next time, I'm just going to use this formula. For each node, I'm just going to go down the column. And for each node, I'm going to sum up the probabilities of all the parents, some of which might be 0. And then I multiply that probability by the node probability itself. And then I can do this for all the nodes in my column. And now I have the alphas for all the nodes in the second column. I can use that to compute the alphas for all the nodes in my third column and the fourth and the fifth. It's a very simple recursive formula, right? And till I get all the way to the end. So this. Now, if you look at the alpha for the node at the bottom right, what is that alpha? That alpha is the probability of all paths that align B phi to the input, correct? So that's basically the probability of B phi, right? It's the probability of every possible way of aligning B phi to the input is the probability of B phi itself given the input. And so this first term, the pink probability, I call it alpha TR. We know how to compute it. So we've computed the forward probability. Now we must compute the, so we've seen how to compute this, yes.
So the assumption that you mentioned, like the conditional independence assumption, that inherently means that we're not considering symbols that occur before.
Because in the neural network, are you? In the neural network, you're not deciding, you're not using what the alignment of was at any time as an input at the next instant. You're just using only the input, correct? That is not being fed back.
But like for tasks like language or like translation and
that we will get to later. You would have to feed those back in. You don't have conditional independence, right? So we've seen how to compute this. Let's consider the second term now. I'm going to call this the backward probability because it's all the paths going back until that node. Now this graph has two initial nodes, so it's a bit complicated. So I'm going to simplify this. I'm going to include that initial, so beta TR, I'm going to call this beta TR. Beta TR is the total probability of all paths leading from TR till the end, but not including the node at TR. Why? Because the node at TR has already been included in the pink graph, right? So all paths except the yellow node. But when you say except the yellow node, it introduces some complexities. So here's what we will do. I'm actually going to include the yellow node and compute my probabilities of the subgraph from and including the yellow node all the way to the end. And then once I've computed it, I'm just going to divide that probability by the probability of the yellow node itself to get it out of the whole equation. This just simplifies the arithmetic, right? So once I do this, it's very easy. The total probability of all paths leading from the 3E node to the end is going to be the probability of going, there are only two, in this case, there are only two ways of going out of this this 3E node, right? You can go from the 3E node either to the green node or the red node. And so the total probability of all paths from the yellow node to the end is either the probability of going from E to the green node and the total probability of the subgraph from this green node to the end plus, which is an OR. You go from here to here, and then the total probability of the subgraph from this node to the end. So it's going to be Y3E times the total probability of this subgraph plus Y3E times the total probability of the subgraph. What is the total probability of the subgraph from here to the node end? Anyone here? What is it? That's just going to be beta for 4E, correct? And similarly, what is the total probability for this guy? This is beta for 4F, right? That making sense to everybody, right? It's very straightforward. And so I can just say that beta hat 3E is going to be Y3E times beta hat, this should have been 4E, correct? This should have been 4E and 4F. So note the mistake, there's a mistake on the slides. But yeah.
Why is the Y3 there? I thought we were dividing that out.
So this is beta hat. I'm including the node.
Oh, then, okay.
Right, because it simplifies the math, okay? And then, so remember, the way we did it was I included the node and then divided it out at the end, right? And so the beta hat at any time is recursively defined in terms of the betas at the next term. This is in fact the same as the forward algorithm with the graph flipped left to right, correct? You could write the code once and just pass in the input in reverse order. So here's what the algorithm is going to look like. You would start at the end and compute the beta for the beta hats for the last column. The beta hat for the bottommost node is going to be just the node probability. You know that the last symbol must align to the bottom right corner, so the beta hat for the rest of them must be 0, right? Then you can take a step back, and now you can compute the beta hat for all of the nodes in this column, where the beta hat for any node is going to be the sum of the betas for all of its children times the probability of the node itself, right? And then you can use those betas at the second to last column to compute the betas at the third to last column and work your way back all the way to the beginning. And so at the end of this procedure, you would have computed the beta hat terms for every single node in the graph. But then the beta hat also includes the probability of the node itself, as was pointed out. So I have to divide that out to get the actual backward probabilities for every node. Is this making sense to everybody? Right, okay. And now once I have these, then it's easy, right? So that's your pseudocode, just going back. So now we know how to compute the probability of the blue subgraph. And so the total probability of all paths that align the tth input to the rth symbol is going to be alpha tr times beta tr, right? But this is the joint probability of the symbol sequence and the alignment, right? So if you compute this product of alpha and beta for an entire column, so if you computed alpha times beta for this node and this node and this node, those products would not sum up to 1. They're just the way, all the ways of aligning the symbol sequence that you have to the input. But you want posteriors, you want them to sum to 1, right? So what we will do is normalize. So you can compute the alpha tr and beta tr for each node, and then you'd compute alpha tr times beta tr for each of the nodes in the column, and then divide by the sum of the same term. And now this gives you the posteriors, which are going to sum to 1. Okay? And so I'm calling that gamma tr. And once you have gamma tr, that problem is solved. My divergence was the sum over all times. And at each time, I was summing over the entire column. And over each column, what I was summing was the product of the posterior probability of the node and the log of the probability within the node itself, right? And the posteriors have been computed. So everything is done. And so now, voila, we have our divergence. Okay. Yeah.
So using the recursion to find the probabilities of each node, given that you know the start and end of it.
It will slow things down, yes. This is going to be slower than just straight up computations, right? Okay, 10 seconds, guys. Actually, I'll give you less time than 10 seconds. I'm running out of time. It's only one question. Someone want to answer the question? What is the answer? Is the first statement true? Yes. Second one? Yes. Okay. So the forward algorithm is used to compute the a posteriori probability of aligning each symbol to each input, the forward backward. These probabilities are required to compute the expected divergence across all alignments of the compressed symbol sequence to the input. So easy. And so now we have this divergence, right? And this divergence is a function of the probabilities assigned to all the symbols, right? And so if I want to, what I really need is the derivative of this divergence with respect to the output of the network at each time, which is basically with respect to the probability assigned to every single symbol at each time. And so I need the derivative of this divergence with respect to any yt, which is the output of the network at each time, is the vector of derivatives of this divergence term with respect to each of the network probabilities. But then, remember, the divergence is actually summing over time and over the symbol sequence. If I want the divergence with respect to the output of the network at any given time, I only need to consider the terms that are going into the divergence at that time, right? The rest of the t's can be ignored. Making sense? Yeah. So these are the terms that we need to compute. But then you have to be a little careful. If I consider this example, I have the word E, right? The symbol E. The symbol E occurs in 2 different rows. So if I ask myself the question, what is the probability that the third input is going to be aligned to the phoneme E? I actually have to sum 2 different terms because E can occur in 2 different locations, right? And so when I compute the derivative of the divergence with respect to the probability assigned to the symbol E, I would have to sum over all of the rows that invoke the phoneme E. Okay, this clear? So the key now is, what is this derivative? And this is the derivative of gamma TR times the log of the probability, right? And just using my chain rule, that's going to be the derivative of, this is the derivative of log of y is 1 over y, right? It's going to be gamma TR divided by y plus the derivative of gamma times log of y, right? It turns out that this guy is really hideous to compute. So when something gets really ugly and difficult to compute, what is your solution? What was it? You pretend it doesn't exist, right? And you find some way of justifying it. And the way you justify it is that this all works out if it's a maximum likelihood solution. And so that's what we do. We throw that block away and we are happy. It works, okay? And the first term is very easy to compute because it's just gamma, which we've already computed, divided by YTR. And so now that means the derivative of the divergence with respect to any given probability assigned to any given symbol at any time is the negative of the sum over all the rows of the table that invoke the symbol of the gammas for those blocks divided by the probability of the symbol itself, right? So the derivative of the divergence with respect to, say, the probability assigned to the phoneme E is going to be 1 minus of 1 over the probability assigned to the phoneme E times the sum over all rows of the gammas for all the rows associated with the phoneme E at time t, right? And so now we know how to compute these derivatives. And we can set up the entire training. And here's how you set up the training. The problem is given input and output sequence without alignments. We must train our models. So we're going to set up the network, typically a many layered LSTM. It could be a bidirectional LSTM or a pyramidal bidirectional LSTM, as you will see in your homework. And then you initialize all the parameters of the network. And then for each input, you're going to pass the input through the network and generate this table of probabilities. Then from the table of probabilities, you're going to extract out the rows corresponding to the symbols in your transcription, in your labels, right? And create this reduced table. And then on this reduced table, you can perform the forward, backward, the alpha, and compute the alphas and betas. And from the alphas and betas, you can compute the gamma. From the gammas, you know how to compute the gradient of the divergence with respect to the output of probabilities at each time. Again, remember that this gradient is going to have zeros for the probabilities of all symbols that don't actually occur in your labels. Only the symbols that occur in your labels will have non-zero values. And then just plug that in. And so this is how you compute the derivative. And then you can now you have the derivative of the divergence with respect to the output of the network at each time. That can be back propagated through the net to train the model. Questions? Yeah.
Gamma was the multiplication of the forward and the back.
After normalization, right? Yeah. So because the gammas in any column must sum to 1. Anything else? Zoom, any questions? No questions. Okay, fine. Let me continue. So the story so far, sequence-to-sequence models which irregularly output symbols can be aligned using Viterbi decoding, or they can be decoded using, I've got to fix that slide too, using a greedy approach. For training, you require alignment of the output of the symbol of the output symbol sequence to the inputs, and it can be performed by iteratively estimating the alignment by Viterbi decoding and time synchronous training. Alternatively, it can be performed by optimizing the expected error over all possible alignments. This is what we've been saying, right? But then there's one key problem that we haven't actually encountered. In all of this, I assume that I could sort of compress repetitions into a single symbol. Compression doesn't always work, right? So look at this guy. I have a decode, 3 R's, 4 E's, or I have an aligned sequence, 3 R's, 4 E's, and the character D. Is this read or is this read? Do we have any way of distinguishing between the two? We don't, right? There's no way of separating the two. So here is what we will do. I'm going to introduce an invisible symbol into my vocabulary. This is a symbol that you cannot see. You know, it's a ghost, but it exists, right? We know this is how it is in real life. So this symbol, which I will call a blank, is now going to be included as part of my symbol sequence. So if my vocabulary were the characters, A through Z, I'm going to introduce this non-character, the empty character, which is basically no space, nothing, it's just blank. But I'll call it a blank for convenience sake, okay? And stick it here. And now when I introduce this character into my symbol sequence, here's what happens. If I performed a decode with using the blank, and I just picked up a symbol sequence, I'm going to get something like AA, B blank, B, 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 C blank, C, C, D, right? So when I compress this, this is going to become an A blank, B, C blank, C, D. This is the compressed sequence. Except when I eyeball it, these things are not going to be visible. And so the actual output is going to be A, B, C, C, D. A, indeed. Right? This is making sense? Yeah.
You will only put the blanks in between characters that you.
No, the blank is just like any other symbol. A blank is just a regular symbol. The only specialty of the blank is that you can't see it. Right? And now I can use this heuristic of compressing repetitions. So when I compress it, the blank is going to be there, but you can't see it. Yeah.
But if your input is like, I don't know, an audio file and it's like
You don't know where the blanks are. We're going to deal with that, right? The problem is in the input, you don't know where the blanks are, but you know how to deal with it in the output. So here we can't distinguish between the extended symbols, so we introduce a blank. And so if you look at the first guy over here, in that case, it's going to be R blank. So the first one is simply going to become R blank E blank D, which becomes red. The second one is going to become R. When I compress it, it's going to be R blank E blank. Is it what? Blank E ED, right? And the blanks disappear, so you're going to end up with read. What is the third one? What does that become? It's going to become R blank R. When I compress everything, it's going to become R blank E blank D blank D, right? And then when the blanks disappear, that's just going to be double R E double D, correct? And what is the last one going to become? Right? Lovely. Okay. So 3 R's, 2 E's, and 3 D's. So you see how the blank works. It's actually there, but it's not there. Yes?
Is there a difference between a double blank, a single blank, and a triple blank?
It's just like when I create a sequence, right? A time synchronous sequence. every single symbol can occur any number of times, right? The blank is a real symbol. You just can't see it. So all of them, so when I have a triple blank, that means that input is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 inputs long. That makes sense? Right? Everybody get what I was talking about, right? Yeah.
If I were to make the graph sort of a structure, would the blank come in the graph or?
It would have to, right? It's a regular symbol.
Yeah, so it can come in anywhere then, because if I'm.
Okay, bear with me. Give me a few minutes, right? So here's a poll. You have only 15 seconds for this one. I'm out of time. Okay, Samya, what's the answer? The last one, right? Easy. Because if you just make the blanks disappear, if you collapse all the repetitions and make the blanks disappear, that's the one that becomes Billy, right? So when I actually perform my inference with my model, that blank is going to be part of my vocabulary. I'm going to get compute probabilities for every single symbol, including the blank. And this is what I will use for inference, okay? But first, so here, for example, if I just pick the most likely symbol at each time, this is going to be B phi, right? But if I got something like this, I'm going to get the blank at the beginning is going to disappear. So this is going to be B, E, then I have blanks and then F phi. So this is going to be B phi as well, right? Something like this actually ends up with 2 Fs because I have a blank between one F and the other F. Make sense? Right. Okay. So now the real problem is training. As who was it you mentioned? You mentioned, right? There are no blanks given to you during the in the training data. So how do you deal with it? Here you have to get tricky, right? The original, I have this hideous example. I always curse it in every semester, but it kind of works, right? So suppose I wanted to have 2 E's in a row. I cannot create this table. This graph makes no sense. This graph makes no sense because if I look at the path, any path through this graph, and compress the repetitions, it's going to give me only 1 E, right? So now I have to explicitly deal with the fact that repetitions can happen, which means I have to explicitly deal with the fact that I have an invisible symbol, which I call a blank, as part of my vocabulary. So here's how I can do this. If I looked at B phi in the earlier example where there was no repetitions, I can think of that as a linear graph, B going to E, going to F, going to E, right? But if I want to have repetitions over here, if I want to introduce blanks, I can have B and E, but I can also have B and blank and E. And as far as your eyeballs are concerned, both are just B, right? Similarly, I can have F followed by E, which means F blank E. And both of them are the same. There should also be an arrow in the middle, which I haven't shown just to show you how things work, right? But the arrow indicates the fact that I could potentially skip a blank. So this path, this graph, represents all possible ways of generating B phi with or without blanks, right? It's missing an arc. But then suppose I want to have B, E, E of this kind, where I have E occurring twice. Then I can go straight from B to E, but I can't go straight from E to E. Because if I went straight from E to E, they would get compressed out of existence. One of them would get compressed out of existence. So whenever I have a repetition of a symbol, I do need to have a blank in between, mandatorily, right? But blanks can optionally occur on either side of every other symbol. So there's this graph on the left making sense, right? And so over here, when I compose the graph to the right, all I'm doing is unrolling the graph to the left, meaning there's an arrow from a node in the table to another node in the table to the right if the corresponding symbols have an arrow between them on the graph to the left. If it's not very clear, look at how this is, right? Here I have an arrow from B to E, so I have this arrow, right? I also have the, I mean, B to blank. So I have this arrow going from here to here, corresponding to the blank row. But I also have an arrow from B to E, which means I have an arrow going from here all the way down here, right? So basically you can think of every row as being a clone of this column, except that the arrows are not downwards, they are diagonally down or diagonally across. It's across time. So is the construction making sense? Yes.
How do you assign probabilities to blanks?
Pardon me?
How do you assign probabilities to blanks?
The blank, so the network computes the
You just treat it the same as a.
the blank is exactly the same as every other character, right? And so here's what happens, right? In this case, I have E. These two are not the same symbol. So from E over here, I can have an arrow to E. I can have an arrow to the blank. I can have a direct arrow going to F, skipping the blank. On the other hand, when I have two E's in sequence, then I can have an arrow from E to E and E to the blank, but I do not have an arrow going from one E to the other because that's going to compress one of the E's out. Yes?
But in this case, you're only able to skip the nodes which are blanks, right, using the edges. Whether the other nodes, like basically B, E, and F, are nodes which you cannot skip.
So you take any path from the top to the bottom.
Your input, you're not too sure whether it's a blank or.
You don't. In the input, you don't have a blank, right? So this is where you get probabilistic. I'm saying, what is the probability that there's a blank at this position? Your forward-backward algorithm is also going to give you that probability. Yeah.
Is the reason that we don't mandatorily put the blank because it messes up the understanding of what a blank is actually supposed to be?
So what do you mean?
Like instead of having the skip connections, if we just have the blank mandatorily.
So the blank is not visible, right? Semantically, the blank is not visible. And if it doesn't matter whether the blank was there or not as far as B is concerned. So you have to consider both options, right? B invisible character E and B character E are both going to look the same to you.
Right.
So you have to consider both options. Yes, Advait?
Maybe I'm missing something, but if there is a repetition in the input, why don't we just add a blank over there?
Meaning?
Like in the input labels.
That's exactly what you're doing. You have a blank. Between E and E, we forced a blank.
But can't you just do that in the input data itself, like in the training data?
It doesn't matter whether you do it in the data or whether you do it when you're composing the graph.
Okay, but you can do it.
You do it implicitly, yes.
So with the fact that you add the skip connection, is it like you're trying to teach the model that the blank is to separate repeating characters and not to separate?
You're saying that the blank is optional between different characters, but mandatory between repeating characters. That's it. Yeah.
Because the input will never have that blank, like audio-wise, when we're saying door, let's say, because there's two O's, but there is no like space in between. Basically, this model with the blanks, after training, will calculate what is the likelihood of one sound being.
No, so you can think of it this way, right? The blank is nothing extraordinary happened at this point. That's all it means semantically.
Yeah.
So when do you actually output the compressed symbols? Whenever you're transitioning from one sound to the other. A blank is saying a transition didn't happen here. That's all it is. It's a nothing happened here symbol.
The blank is saying something, a transition happened here, right?
A transition didn't happen here because you're right. Your blank, what is the blank saying? The transitions can happen where the symbol is actually generated, right? Mm-hmm. And if there's a blank, then you're not outputting any symbol. Mm-hmm. So there is no transition at that point. So the blank is saying a transition didn't happen here. When you see a symbol, it means a transition might have happened here. When you see a blank, a transition definitely did happen here. Yeah.
So your model is training, for example, and let's say you have 9 time steps here, and then the first 3 time steps is just the node B. So how does the model know that it's not multiple B's?
The first 3 time steps are not B, right? Your symbol sequence, your label is simply going to be B phi in this case, or BE in this case.
Let's say it goes from YB0, YB1, YB2.
That's one particular alignment. Okay.
Yeah, for that particular alignment.
The point is we don't know what the alignment is. If you're given the alignment, no biggies, right? You can always train the network. The issue is really where you're not given an alignment. Okay, yeah.
Why don't we mandatorily skip the blanks between B and E? Because it's not.
I'm saying that it's not, the point is the blank is essentially an invisible symbol, which means that unless you're informed, you don't know whether it was there or not. So you have to consider both possibilities. Yeah.
I know we treat it like a symbol, but why would you have connections like from blank to blank?
You don't. There is no connect. Only horizontal, right? They're repetitions, but there's no connect. You don't never skip from a blank across a symbol to another blank.
But even horizontal doesn't have.
So horizontal is like saying I have a sequence of nothings, right? So.
Okay.
Yeah.
Why are we doing skip connections? Why don't we do the blank mandatory between like every other symbol?
If you
by compressing, it would just
So the blank is an invisible symbol. You can't really say whether it's there or not, right?
Yeah. So like.
So yeah. So you could enforce a blank between every pair of symbols, but practically you will find that that doesn't work very well. I mean, there are, for example, very short. If I was thinking in terms of speech, there are very short sounds where you really don't have room for a blank before the sound. Yeah.
So in that scenario where you don't have room, the likelihood that the blank will be there will be quite low, right?
Very low. I mean, yes. So again, empirically speaking, you can test it out, right? These are things you don't have to discuss, just test it, right? And so once you compose this graph, training is simple. Now observe that you can have the first column can either be a blank or the symbol itself, because you could lead with a blank. The last column could also either be a blank or the symbol itself, because you could have trailing blanks, right? Besides that, nothing else changes. You have skips permitted across a blank, but only if the symbols on either side are different. And then you never have a connection from a blank to a blank skipping a symbol, because that symbol is definitely part of your label, right? And so that's how this graph is constructed. If you look at the graph, from any blank, you have a connection, horizontal connection to the blank or a diagonal connection to the next symbol. From any valid symbol, you have a horizontal connection to the symbol, to the blank following. And if the next symbol is not the same symbol, you have a skip connection. That's it. The rest of it is straightforward. Now we can just modify a forward algorithm. In the forward algorithm, you're going to have symbol probabilities for both of the first two nodes, right? And then as you go forward at each time, at each node, you're going to be summing the alphas over all of the parents and then multiplying in the node probability. And specifically, if you look at this, so the sum of the alphas, you're definitely going to be in any row L at any time, R at any time T, you're definitely going to be summing alpha T minus 1 R, which is the alpha in the same row. Okay, so that's just going to be the alpha in the same row at the previous time, right? And this is that is the horizontal connection, and this is the alpha in the previous row at the previous time. So those two are definitely there, and if the symbol over here was not the same as the previous symbol, then you're also adding in the alpha 2 rows earlier at the previous time, right? And then once the alphas are added, you just finally multiply in the node probability itself. So you just use this thing to compute the alphas going from the beginning to the end. Similarly, if you want to do the betas, the beta hats are going to have non-zero values for the last two elements in the graph, and the rest of them are 0. And then you work your way backwards, where for every node, you sum in the beta hats for the children. Some of them will have 2 children, some will have 3, depending on how you compose the graph. So for any node where the subsequent symbol is not the same symbol, for the blanks, they're going to be only 2 children, that row itself and the next one. For the symbols, if the next symbol is not the same symbol, then you're going to have 3 children. Otherwise, if it's a repetition, you have only 2 children. So you add those 3 betas and then finally multiply in the node probability. And then eventually, when all the beta hats are computed, you divide by the node probability itself to get the betas. And the rest, the gammas and such like, are computed exactly as before. So nothing fancy. Questions? I'm going to go a little over, but yeah. Any questions? So do we understand how we deal with blanks? Go back and look at the slides if it was not clear, right? So, and so the overall training, you would now be given an input of this kind with input and the symbol sequence. You would be adding the blank to your vocabulary, keeping in mind is that the blank is an empty sequence, is an invisible symbol. And then you'd initialize your model. And the model is going to generate probabilities for all of your symbols, including the blank. And then for every training instance, so when you perform a forward pass, you get all of these probabilities. Then you would compose this graph, which also now has the blanks, the invisible blanks. And the blanks are going to mandatorily occur between repetitions of a symbol, but are optional between symbols that do not repeat. And so if you look at the edges in the graph, you never have a connection from a blank to another blank further down. So from blank rows, you only have 2 outgoing arrows. From the other rows, you have at least 2 outgoing arrows. And if the subsequent symbol is not the same symbol as this one, then you have 2 outgoing arrows. So you compose the graph, then you perform the forward-backward algorithm to get the alphas and the betas, from which you get the posterior probabilities, from which you can compute the derivative vector, the gradient vector, which you can back propagate to train the network, right? So everybody clear? Easy. The overall framework we just saw is referred to as CTC. It applies to models that output order aligned but time asynchronous outputs. So now here's a problem, right? We said that the manner in which we performed inference, we said was greedy, right? But then when we performed greedy, initially we had the issue that we couldn't distinguish between repetitions, but once you introduce a blank, that problem has gone away, but you're still left with an issue. So let's say I have these possible decodes of an input which is 6 symbols long, right? So I find that RR blank EED has a probability of 0.7. RR blank blank ED has a probability of 0.68, and REED has a probability of 0.69. I also get probabilities for sequences with T, E, and D, and I find that TED with no blanks has a probability of 0.71. But the other alignments of TED have very low probabilities. If I pick the most probable output, which one would I pick? But which would make more sense? Red, because across all options, red is actually more probable, right? So you really don't want to be picking just the greedy output, although it works most times. You want to pick the symbol sequence for which the total probabilities across all alignments is maximum. And so, greedy decoding, it turns out, can be actually surprisingly effective when you're decoding with blanks. Here's a very nice picture from Graves' original paper on this framework. And they show that if you just perform a greedy decode, whenever you have extended phonemes, the blank tends to be the most likely output. And these phonemes actually sort of pop up exactly where transitions happen. So just doing a greedy decode very often just gives you very nice results. But doing the right thing by picking the most likely, picking the symbol sequence which has the greatest probability across all alignments gives you better results. But then, what exactly are we doing over here? You want to pick the symbol sequence, the compressed symbol sequence, whose length we do not know, right? That has the highest probability given the input. This is the actual inference problem that we would like to solve. And our problem is that we don't know how to compute it because the number of those sequences is exponentially large. So we don't, but then how do you compute this probability for each sequence in the first place? To compute the probability for any given sequence, we already saw how to do this. If you give me a sequence and ask me what is the probability, then I can just compose my graph with blanks. Here I'm not showing blanks, but you do it with blanks, right? And then the alpha at the bottom right is going to be the probability of the sequence itself. If you had blanks, then you'd have to sum the final 2 alphas, and that is going to be the probability of the sequence itself, right? And so if you want to perform inference and say, I want to pick the symbol sequence that has the highest probability, you'd have to compute this bottom right alpha term for every symbol sequence that's possible and pick the symbol sequence for which this alpha was highest. Is that going to be feasible? There's an exponential number of such sequences, right? So which one do you choose? Dynamic programming to the rescue again. But first, here's a poll. I'm going to go 4 minutes over, bear with me. And this poll is only 30 seconds long. The phone won't beep, but yeah. Ishani is going to go beep, beep. 5 seconds, guys. Beep, okay. So is the first statement true? Second one?
Yes. True.
Right? The actual objective of decoding is to identify the unaligned sequence that has the highest probability given the input. This is the same as finding the compressed sequence with the highest alpha for aligning the final symbol in the input to the in the sequence to the input. The problem is with computing the alphas, right? Explicit computation of this is going to require evaluation of an exponential number of symbol sequences. So here's what we will do. We're going to organize all possible symbol sequences in a semi-tree. But when we organize it, we're going to also include the blank, okay? So look at this. Suppose I have a vocabulary which has just 2 symbols. Then what are all the ways of generating just one symbol, which is either S1 or S2? I can either just have the symbol be S1, or I can have a blank followed by S1, right? I can have just the S2, or I can have a blank followed by S2. So all 3 of those can be represented using this little tree, right? Now, what are all the ways of generating S1, S2? I can extend that S1 to an S2, right? But then I can also have what are all the ways of generating S1, S1? For S1, S1, I mandatorily need a blank in between, right? But then actually, I can also generate S1, S2 in this manner, right? So this represents all possible ways of generating S1, S2, right? Similarly, the bottom one represents all possible ways of generating S2, S1, and S2, S2. So now this tree represents all possible sequences of length 2, right? There are 4 options, S1, S2, S2, S1, 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 S2, S2, right? And this represents every possible way. So if I didn't have a blank, it would be a pure tree. But because I have this invisible blank, I have to account for going through the trees, right? And the blank is what separates the repetitions of any symbol. So is this making sense to everybody? Yeah.
Aren't the blanks supposed to be connected to themselves as well?
So this is just the tree of symbols. This is the tree of compressed sequences, right? All possible compressed sequences, except I'm also representing the blank. Is that making sense? Right? I'm not speaking of repetitions. I'm not speaking of time synchronous sequences. This is the tree of compressed sequences where I explicitly also represent the blank. So this is what you would do before you erase the blanks from after compressing things, right? And so, yeah.
You represent that the root line can be skipped.
So we'll see. I'd actually have, I'd need an initial dummy node which points to the root blank and the S1 and the S2. So I haven't gone through that, okay? And then I can extend this onwards. If I want to consider all symbols of length 3, then this goes on, and every node at level 1 is going to get extended by basically a replication of the same tree. And this entire tree, it's not a real tree, it's a semi-tree because I have these loop backs, right? But this represents every possible way of representing every possible way of, every possible compressed symbol sequence, including blanks. And so now, just as we composed this trellis earlier, where I just, remember, when I was doing a forward, backward, I just had this, where was I? I had this compressed graph to the left, right? I had the graph to the left and I just unrolled it over the input. Instead of having that graph, I'm now going to use this tree on the left-hand side, and I'm going to unroll the tree across time, okay? So if you look at this, now this node, look at this guy here. This row over here represents all symbol sequences that are exactly S1. This row represents all symbol sequences that are exactly S2, right? This row, the only way to get to this row is to go from here to this blank to S1. So this row represents all symbol sequences which are S1 blank S1, right? So every row over here represents a unique symbol sequence. Is that making sense? Right? And now once I have this, I can just go forward and perform my forward algorithm left to right till I run out of symbols. What would the problem with this be? The size grows exponentially, right? How would you deal with that? Greedy is already beam search, right? So what I can do is start off. So what I would do is to actually use this graph, compute the alphas all the way to the end. Then at the final instant, I can compute the alpha for every symbol sequence. Every symbol sequence is going to have two variants, just the symbol sequence or the symbol sequence with a blank at the end, right? And so I can just compute my alphas. I'd start off with the top left and at the bottom left, and then I'd compute the alphas for the entire first column, but then I just retain the n best nodes. And the rest that are too poor, I'm going to delete. And so in this case, I'm retaining 5 nodes and I'm deleting 3 nodes, right? Then I'm going to expand only those surviving nodes. I'm going to have a whole bunch of nodes. Then from these, once again, I retain maybe the best 5 and delete the rest. So at each time, my computation is bounded because I'm always retaining only 5 nodes. And I can go all the way to the end. And eventually, I'm going to get a bunch of alphas, which I can group up to find which sequence had the highest probability. So this is the classic beam search algorithm. So I have pseudocode for it on the slides. Go through and there are a lot of tricks for the beam search itself. And I have some very devious and detailed, pseudocode, but then my TA Jichan a few semesters ago came up with some very devious code, which is 1 slide long, but nobody understands it. And so we'll post that on Piazza, okay? It's part of your homework. So the story so far, sequence-to-sequence networks which irregularly produce output symbols can be trained by iteratively aligning the target output to the input and time synchronous training, or optimizing the expected error over all alignments. Distinct repetitions can be distinguished by the introduction of this invisible blank symbol. And decoding can be performed by best path greedy decoding or using the beam search algorithm, right? That shouldn't be bitter B. That's an error. Skip this. Most common application, speech rec, handwriting recognition. But anyway, take a look at the slides. We are done. I'm running over time. Thanks for your patience. And what you didn't learn in class, you're going to learn from your quiz.